Okay, good morning. Today we have a fairly short seminar by Sara Bertran. Sara is a student here at the IC. She studied physics in Madrid and then did her master's in astrophysics there. And now she's pursuing a PhD here on spectroscopy and stellar spectroscopy using 3D models to compare what changes in the abundances can be expected if one compares the classical analysis of stellar spectra in 1D with those in 3D with hydrodynamical models. But before doing or getting immersed in her PhD topic, she took a detour and explored some studies of oxygen in the disk of the galaxy. First using her own spectra and data from HARPS, and now with APOGEE. And with APOGEE, she found a very exciting discovery that the cosmic dispersion in oxygen over iron in the disk was quite small, and she's going to tell us all about it. Sara.
Is mute, okay. So, the cosmic variance is when you measure a certain ratio of abundances. It can be oxygen, but it can be anything else. You will measure two different components of the. Well, your measurement will have two components. One to the scatter. One, it will be the errors, so the intrinsic errors of the measurement, but you will probably also have a contribution from a cosmic scatter, which means that this ratio of abundances is not the same in all the galactic disk. So basically, when you try to measure the cosmic variance, what you have to do is to push your errors down enough to be able to detect this cosmic variance. And why is the cosmic variance useful? Well, because when you have two metals produced in different sites, it can be, for example, oxygen comes from supernova type 2, iron comes from this and also from type 1a. So if you measure the ratio, you can have a lot of information about the chemistry and the evolution of the chemistry in the galaxy. And that's why we want to measure it. So there were people, the first one, Edwardson in '93, who tried to measure this cosmic scatter. So he measured for almost 200 stars in the solar neighborhood, dwarfs, and this is what he found. So basically what he says is that there is almost no scatter in alpha elements over iron at a given galactocentric distance. But he found when you go down in metallicity, he found some scatter, which was much larger than if you go to higher metallicities. And that's why, that's because by this time, they didn't know that the chemistry of the thin and the thick disk was different. Then, Reddy in 2003, he already knew this, and he selected a sample of thin disk stars, also more or less quite similar sample than Edwardson, 200 dwarfs. And he concluded that the scatter at these low metallicities was due to the mixture of these two populations, the thin and thick disk. But this cosmic scatter was not detectable but in his thin disk stars. So he tried to do something funny, that was to predict the theoretical errors, which are in the x-axis, and he also measured the scatter, which is in the y-axis. So when you do this, you have two different regions. you can have in the red one means that you are basically overestimating your errors because the scatter that you expect is much larger than the one you are actually measuring. But in the green area, it can be two possibilities. Either you are underestimating your errors, and that's why you are measuring a larger scatter, or you are actually detecting some cosmic scatter. In this case, he is probably underestimating his errors. And if you are in between, and here is where almost all the alpha elements are lying, it means that you cannot say anything. So your estimated errors are more or less the same as the scatter you are measuring. So since Reddy didn't have any thick disk scatter, I think this star, he looked for another samples and he put everything together. And he then measured some kinematic properties of these stars. So the black dots are the thin disk stars from Reddy, and the other stars were thick disk stars from other studies. And here you can see how, although it seems that the thin disk stars are different from the thick ones, in the kinematic properties, they overlap. So you cannot really distinguish properly. And we will use this in a few slides. So, more recent studies also attempt to find this cosmic scatter, and here the signal to noise are much higher, resolution are much better, and all these studies have around 1,000 stars, but still they couldn't find and they couldn't measure this cosmic scatter, which means that it's not about having more resolution or more signal to noise. Here in this right upper plot, the stars, some of them have close to 1,000 signal to noise, which is amazing signal to noise, and resolution more than 100,000. So it's not about resolution and signal to noise. So we tried something different. So we tried to use the APOGEE sample, which has in total like 160,000 stars. And within these stars, and it covers, if you look to the plot, it covers a really big range in galactocentric distances. So it's a huge sample. The resolution is high resolution, but still not that high. And the signal to noise, we cut for having a signal to noise about 80. Is spectroscopy in the H band, so it's infrared. And we measure the oxygen using OH bands. So we made some cuts in stellar parameters to avoid some systematic errors, to have giant stars. And also we cut in metallicity to have this range where you can have both thin and thick disk at the same time. We also made some cuts to avoid the halo stars and also bulge stars. And so now we face the problem again of how we calculate the uncertainties, because this is the key point. If you want to detect the cosmic scatter, you have to measure the uncertainties pretty well. So here you have a big problem because you have many sources of error when you calculate the abundances. So you have errors in your equivalent with measurements, or if you are fitting the spectra. You also have errors in the continuum placement. Sometimes there are undiscovered blends in the spectra. Then you have problems with your models, of course. The oscillator strengths of the lines are sometimes uncertain. You have errors in your fundamental parameters. In your models of atmospheres, you can have 3 effects, not an LTE. So you have a lot of sources of error, and calculate and put all together sometimes is really hard. And especially what people usually do is just combine all them together, so add them. But sometimes they are not added, so you tend to overestimate your errors because they can, so one can be added, but the other one can compensate. So the good thing of APOGEE is that we have clusters. And clusters here are really useful because a cluster is a single population. It is formed in principle at the same time, so you will not have cosmic variance in your cluster. So what we did is measure the scatter in the clusters. So the scatter in the clusters will come only from the errors in the measurements. So we select several clusters, and we did some bins in temperature and metallicity to avoid systematic errors. And we calculate the scatter in each bin for each cluster. And we fit a polynomial. So our range of parameters is the one marked within the dashed line. So there you can see that we are reaching errors below 0.02 dex in oxygen over iron. So once we have the uncertainties problem solved, we will take a look to the sample. See, sure. Can you repeat, please? Yeah. We have both, because when you go low in metallicity, you will also have globular clusters. That's why, so yeah, there you can have some cosmic scatter, but the thing is that we almost don't have clusters in our range of parameters. So we have to extend it a little bit to properly fit a polynomial and estimate the errors. And that's why we decided to have also some globular clusters, although, of course, the scatter will grow there a little bit. But still, it will be useful to estimate. So it will be an upper limit of the errors, anyway. So, well, if you take a look to the sample, all combined in temperatures, it looks like this. So you can almost distinguish by eye the two populations, the thick disk above with the alpha, the oxygen enhanced, and the thin disk below. So we try many things to separate these two populations. We try clustering algorithms. We try, well, many things. And at the end, what we find to be the most useful and easy solution is to bin the data in metallicity. So if you bin the data in metallicity and you create an histogram, you can perfectly fit, or more or less easily fit, a double Gaussian. And this is quite useful because fitting this with all the parameters free, you can have at once the mean of the population, the scatter, and you can separate both disks. So what we did is fit this double Gaussian and put the separation where the two Gaussians cross. And we did this for several bins of metallicity. So what we did was something like this. So in the first one, you mean? Well, I cannot stop, but I think so. Well, yeah, let me try. Here we go. So at high metallicities, we only have thin disk stars. Yeah, there's something small, but not even remarkable to fit it, and I don't think it's going to affect the mean. Anyway, when we calculate the scatter, we are going to avoid these high metallicities.
No, I mean, my point is that to see whether it keeps going down or just stays stable. That between 0, let's say, and 0.2.
I can go like this, one by one. So here you have something, and here you are able to actually fit the second Gaussian. Then it goes.
So at 0, it's above oxygen over iron is like 0.05 or so. At 0.
Mm-hmm.
Not 0.
You mean here? The mean value, you mean? The mean value for the thin disk, it's slightly above 0, yeah. Yeah. Anyway, we don't care that much about the mean value, but about the scatter. And you will see that, well, you will see that here you can fit it much better. And, well, you will see later that the scatter is more or less the same. So even you have some errors, and we also calculate the errors, because we have, so in this histogram we have errors according to the number of stars. when we do the fit, we take into account these errors, and we afterwards get some errors for the scatter. So, well, so once we have this scatter measure, of course, you have some effects that can make it different. The first one is the signal to noise. Of course, if your signal to noise is better, your scatter will probably be also better. And we also wanted to check if the signal to noise of the clusters are representative from the sample, because clusters are, in principle, better observed or can be better observed. But we found that the clusters, in principle, are a good representation in signal to noise of the sample, and that, yes, if you go down in signal to noise, of course, your scatter will go down, but it will reach some plateau after 200 signal to noise. And another thing that you have to take into account is that you have some gradients in your galaxy. So you will, in metallicity, for example, you have a big gradient in galactocentric distance, and also when you move up and down from the plane. So we wanted to check in oxygen over iron if these gradients also exist and take them into account. But, well, we measure them, and it turns that they are almost flat. Still, we try to compensate this and recalculate the scatter, and it doesn't change at all. So the galactic gradients of oxygen over iron are negligible for the scatter calculation. And we finally came to a plot like this. So here you have for 3 different bins of temperature, and for all the metallicity bins, the scatter that we calculate. You have a green line here, and it's because there is another effect that is the chemical evolution, so the age of the stars. And of course, you will have some scatter coming from the age, because it's not the same as quite old star than quite new star. So Nielsen measured this scatter in the solar neighborhood in stars in 40 parsecs around the sun. And he found that this contribution is more or less 0.02. So of course, our APOGEE stars will also have this contribution. But the scatter that we find is slightly bigger than this, which means that if you take a big range of galactocentric distances, you will have another contribution, not only the age. And here in gray, well, the black and gray area is the errors that we calculate with clusters. So the scatter that we measure is way above these errors. Well, so, sure. It's separated by temperature because in the APOGEE data, it's quite probable that you have some systematic errors in temperature. So if you bin the data, you avoid these systematic errors. And since you don't care about the mean value, which is probably different, for the scatter, it doesn't matter. Well, so now that we have the scatter, we want to play a little bit to see how useful is this information. So we built a toy model. And so we assume that supernova type 2 explodes, and the speed of the envelope is 10 to the 3 kilometers per second, and it takes 10 to the 4 years to completely mix with the interstellar medium, which means that it covers a region of 10 parsecs in radius. So this is a toy model, of course. There are many things that we are not taking into account here. And the supernova yield more or less 1 solar mass of metals to the interstellar medium. So this means more or less this 10 to 26 kilograms per parsec cubic of metals. So the first supernova will raise the metallicity of the interstellar medium to minus 0.3, or minus 3, excuse me. So if you take this and you build somehow a galaxy disk, which is 15 kiloparsecs in radius and 1 kiloparsec in height, you will have 10 to the 8 zones of this 10 parsecs radius inside it. So if you take a rate of 0.01 supernova per million year in each zone, it will mean that in 10 gigayears, you will have in total 10 to the 10 supernovas in the whole disk of the Milky Way. So if you assume a binomial distribution of this supernova in each zone, you can calculate the mean. You will have 10 to the 2 supernovas in each zone in these 10 gigayears. And you also will have some standard deviation. The standard deviation is 10 to 10 supernova per zone. And if you translate this to the scattering metallicity, it will be 0.04 dex. So of course we have tuned this 0.01 supernova per million year per zone, so we can have the scatter that we are finding afterwards in our calculations. So we can make a kind of a simulation and take 100 zones. So we will distribute these supernovas randomly in these zones, and we can check how the metallicity is rising and how this scatter is changing. And so in each of these X columns, you have one box. There you have the time passing, and here is how the metallicity is rising. And if you take a look, you will see that the metallicity is getting more and more homogeneous as time passes. So now you can take a look to the scatter. So if you calculate the scatter at each time across all the zones, you will see how it drops up to 0.01 scatter, more or less. And at the same time, you can measure the scatter inside each box, but average along the time. And what you find, so the black line is if you take into account all times, and the red line is if you only take into account from 2,000 million years and to the recent time. And what you found is the scattering metallicity in some area, for example, the solar neighborhood, will be 0.2 dex, which actually fits quite better with what we found when we measure it. Yeah, it's a closed box, and it's very simple. Of course, we miss a lot of effects on it, so this is just to play a little bit with the numbers, but it's nothing else. So our conclusion is that we detect a cosmic scatter in oxygen over iron. See. What do you mean that what do you mean? It's, yeah. I don't understand. Yeah. 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 So, yeah, exactly. What you do is, no, we don't get we are just calculating the scatter at each time across all the zones. Okay, so our conclusion is that yes, we detect the cosmic variation in oxygen over iron in both the galactic thin and thick disk. When we look to for the first time to a big region in galactocentric distances, this scatter is about 0.03 dex. The spatial gradients in oxygen over iron are negligible. And we conclude that the cosmic scatter can be a good estimate or a good constraint for models of galactic enrichment. So that's it.
If there are questions?
I have two questions. One is connected to the number of supernovae that you have used, which is 10 to the 10. So our galaxy has 5 times 10 to the 10 solar masses. So assuming 10 to the 10 supernovae is not a huge number.
Yeah, that's part of the thing, that you really need much more supernova to
But
reach.
is it realistic to consider that 1 in 5 stars has been supernovae?
I don't know if it's realistic. I'm not doing this kind of stuff.
No, but I mean, just to, because that would imply that the AMF is completely different than what we have today, because...
What we have is that, I mean, this rate is 1 supernova per year in the whole galaxy.
And the other question that I have is connected to the migration of the stars.
Mm-hmm.
So this is supposed to be quite relevant,
Yeah.
and I was wondering whether what we are observing here is not just an effect of the migration. So whatever you form the
Yeah.
stars with the chemics that they have, then at some point they will mix well enough, no?
Yeah, of course. So when you look to this plot, here, so from this red line that is supposed to be the contribution from the age, you have room for much more effects. So of course migration can be one, outflows can be another one. So the thing is that when you measure this scatter far beyond the solar neighborhood, you have more scatter, and we think that all these effects appear here also. Of course, they are small.
Any more questions?
So this is actually related to Giuseppina's comment earlier. So in the open clusters, do you see any evidence you see no evidence for spreads in oxygen at all in these open clusters?
Yeah, we see.
Okay.
So
Because this is an interesting aspect, because as Giuseppina mentioned, you do see these large intrinsic spreads in globular clusters.
But so the thing is that your uncertainties also grow when you go lower in metallicity, and also when you go higher in temperature. So we are not sure if this is because just the errors grow, or probably because there is also some cosmic variation in there.
Okay, okay.
It's, again, a question that had to do with my previous question.
Yeah.
And the fact that you use a closed box model for the toy model, it means that the scatter that you infer is only a part of it. Because gas is going to flow in and flow out, and we know. And there are many evidences that this has been happening in our galaxy.
Sure.
And so somehow this very high rate of supernova that you are using, that was mentioned before, maybe it have to be smaller, and at the same time you have to how to add statistical fluctuations which are not due to individual supernova explosion, but the fact that it's not a closed box. So.
Yeah, of course. But also the scatter that we are finding with this toy model is actually lower than the one that we are measuring. I don't know if this will be significant or not, but what we are reaching is something below 0.02. And what we are measuring is something about 0.03 or 0.04.
Then perfect, because it means that you have to add something else. And this something else, at least these two things, in and out thing, gas flowing in and out, is something that is there.
Thank you.
Any additional questions? No? Okay, then we'll call it a day. Thank you.